You can see my screen, right?
Yes.
Yeah. So if I, yeah. So last day, let me remind something what we learned so far. So last day we understand how to download Casa and install it in our laptop, and then the first task we did is that we have this small data file in .fits format, which is given by the observatory to you. And first task we have done is import UV feeds, which is basically converting your data into Casa readable measurement set that I gave it here in the VIS option. So Casa is basically a software tool to reduce the radio dataset, and it has a Python interface, and it is a very well documented. And for every task, there are some options, and and the short description is also mentioned in the right. So after this doing import EV feed stuff, what we have done, we have run the list of stuff that is basically giving you or telling you what is your data content. So what are the calibrators you have, from which time range to which time range you have observed the flux calibrator, phase calibrator, and target. How you are observed it, like you in the beginning you observe flux, then phase, then target, then phase. What are the frequency information you have, that is how many channels, what is the channel width, and from that we find out what is the bandwidth also, and what is the time resolution, that is the correlated downtime, that we also found out yesterday. This is the list of stocks output, and here we have seen that. So we observe 3C286 in the beginning, which is flux calibrator, then phase, then target, then again phase. This is the time integration, that is the after each 8 second we averaged our data set. And these are the scans, right? The first scan is on 3C286, the second scan is on phase, and then target, and then again phase. And here the time range is also provided, this how long your the scan length, right? So you have observed almost 40 minutes for the target, say some 5 or 6 minutes for the phase calibrator, and so on and so forth. We also find out this RA deck, from the RA deck, which one is the flux calibrator, which one is the phase calibrator, and which one is the target. And here the information of your frequencies are mentioned, that is the channel, how many channels you have, what is the frequency of your fast channel, what is the frequency of the central channel, what is the channel width. So that we have learned yesterday, right? We have noted it down here, what are the information we get from our measurement set. And also we've mentioned that let's say you want to observe for the first time, you have to tell the observatory which flux calibrator, phase calibrator you want to observe during your observation in any cycle. And that can be find out from this nice tool. If you provided the RA and DEC here, it will tell you what are the calibrators are available for that particular observation. VLA also contain all the flux values and of the different calibrators here. So these two links provided here. And then we show this antenna position coordinate of the GMRT, that's the small data set which we have provided to all of you. It is a GMRT data set at 608 megahertz. And from that we run the plot and task inside the casa, and it will basically giving you the antenna position, which basically tells you it is a Y-shaped pattern. Here is a central cone, and there is this long arm and these two short arm, right? Then we ended up here, that is the elevation versus time. So we show you that there is a nice tool inside casa which is called plot ms. And in the plot ms is you are able to plot your data set in various way, and it is a very user friendly graphics based tool. You can choose different option here, like calibration, like data, in the data you can provide the field id, that is whatever you want to plot, the time range, the uv range, the antenna scan, everything you can provide here. By clicking on export, you can actually export this image, that is you can save that image in your data folder. Then you can provide the different axis option, like in x axis I have provided here time, and in y axis I have provided elevation. That again tells me that in the beginning I observed a calibrator, flux calibrator here for this time range, then I observed phase calibrator, then target, and then again phase. And different color basically tells you the different field. And how I did it, basically I clicked in this display option, I colorize this by field. Okay, so that is basically color the different field in separate colors. Like here is black, magenta, and orange. And this is a plotting tool which we can use for to generate different kind of plots. But what we found last time that it is taking a lot of memory and it will take some time. So today I am not going to plot anything. I will just show you different options, and I will show in slide what are the plots we will generate via this plotomista tool. Okay, and sorry, here it is. If I okay. So next, as I told yesterday that this one is our original dataset. That is for a small GSB dataset. We cannot provide you a large dataset. Basically, the size will be huge. But I have already worked on some GWB wideband large observation, which this is an 8-hour observation, and this is how the elevation versus time plot looks like. So this black one are the flux calibrator. So I in the beginning I observed a flux, and then another in the middle of the observation there are two scans, and in the end of the observation, since this flux calibrator goes down below 20 degree, that is there is a rise and there is a set, right? When you observe some source, that source like sun, it will rise and it will set. And since this flux calibrator, this particular flux calibrator is going down, so at the end of the observation we observe another flux calibrator, and here it is the phase and target, phase and target, phase and target, like that. So we have a scan on phase, then target again, then another phase, then another target again, like that. So this is a 8-hour synthesis observation using UGMRT at band 3 from 300 to 500 megahertz. So this is just to show you how a real observation, a long real observation will look like. Okay. Now you can generate the UV coverage plot. Here in the x-axis, I have plotted the U wave. In the y-axis, I have plotted the V wave. And these plots have been generated using plotomestas, right? And these different colors are basically tells you for the different calibrator. The black one is for flux calibrator. Again, the magenta one is for phase calibrator, and the yellow one is for target. And this is for from your data set. You can always take a homework from that. You can generate this kind of plot in your laptop with your own data set. Okay, so what it tells us that it is these different tracks is basically corresponds to different field, and since the array deck positions are different in the sky, these are basically sampled different UV space in this UV domain, U wave and V wave. So that is one thing we know so far from this image. And also it is hard to understand the earth rotation synthesis here from this particular plot, and also the how the bandwidth will affect your UV coverage. But I will show you in little time that how it will happen for the wideband data set. Okay, so
So
I
Arnab, can I ask something?
hmm, hmm, hmm.
So just go back to the, yeah. So I see the black dots have very large UV values, which doesn't even come near to these orange and red points. Why?
Yeah, so the answer is here. Basically, you see that your flux calibrator 3C2AC, it has an array and deck. This deck position is far offset from your phase
Okay,
and
okay,
target.
okay, 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 okay.
So
Fine.
your
Sure.
UV, yes, your UV coordinate are basically depends on your array deck position, right? Whatever you
Correct.
are observing your sky, it is just a Fourier transformation, and it this coordinate transformation basically, and this is basically due to that,
Okay, okay.
right? And yeah, let's move forward. So here I have plotted in a separate way. That is, first I plotted the flux calibrator in the left column, and in the right column I have plotted the phase and target. Here it is again clear that the phase is closer to your target, right? Not exactly coincident, but it is closer. So that is why your when you go come to UV domain from the sky domain, you see that these tracks are nearly consistent or nearly close to each other. But however, the flux calibrator is a little bit off. Okay, and that is basically there is a significant difference in deck. Now try to let us try to understand what earth rotation synthesis using the large wideband data. So I have a wideband data, I generated this kind of plot, And let us try to understand what this looks like. So here I have again plotted the u wave in the x-axis, and in the y-axis it is a v wave. I just plotted a single channel that is at a single particular frequency, and I have plotted a single scan also. The scan length is 25 minutes. So you can see that there is a small arc corresponding to this 25 minutes observation. So your earth is rotating, whatever your visibility points are basically giving you the each baseline. So each point is corresponds to a baseline. A baseline is basically constructed from correlation between two antennas, right? Now your earth is rotating, you have observed a particular target for 25 minutes scan, and so your that this point you will get some shift, and it is just a rotation, right? As you can see, every point is basically rotating for 25 minutes. Now let us include two scans now, each of 25 minutes. So now we have a 50 minutes observation. As you can see that it has rotated more, right? And that is basically your earth rotation synthesis. So you, whatever your goal is, that you want to synthesize this uv space via as many points as possible. So one way to do is use the earth rotation, observe a target for long time. So that in that way this will create a track, a circular track, or it is basically rotating in your uv plane, and it will fill up your uv space. So that is one motivation to do this synthesis imaging via radio interferometer. So via this way, if I add more scan, like three scan each of 25 minutes, now I have added 75 minutes of data. It is more, it has rotated more. So if I go ahead, and if I plotted the 7 scan for a particular single channel, it is rotated mostly, and it has created a nice uv coverage in your uv domain, right? And these are the total number of scans. So this is a wideband data set. I have total 8 scans of my target in that data set, and I have plotted all the 8 scans, and different color basically corresponds to different scan. And I have plotted a particular single channel. There is no bandwidth here, okay? Try to remember that there is no bandwidth. I am just demonstrating how earth rotation, that is if you observe a particular target for longer enough of time, how this earth rotation will cover your uv space via earth rotation synthesis. Now let us try to understand effect of wideband. Now what I have plotted here, I plotted the single scan of 25 minutes and a single channel from our observation wideband dataset. Here what I have plotted, that again the single scan, but a 512 number of channels. So what we can find out, that it is radially stretching, right? So this is a single scan, that is there is no earth rotation for beyond 25 minutes. However, I am now increasing my bandwidth, that is I am increasing the number of channels. So here I have plotted, earlier we used to see that we plotted the single channel, and we rotate the we use earth rotation synthesis via plotting a longer observation, and we found out that it is basically covering your uv plane via rotation, okay? That is a circular tracks it made. Now if I take a single scan, and I increase my bandwidth, not the single channel, now I am adding up more and more number of channels. What will happen, it will basically radially stretched. Now you can ask me later, or you can yourself try to answer this question, why it is radially stretched if I add more and more number of channels. That is, if I increase the bandwidth, why the data points are radially stretched, okay? So here I have plotted 512 channels, then 1024 channels. As you can see, this is more radially stretched. All the data points are radially stretched. And then I have added all the 4096 channels. So in my data set, I have 4K channels, and I have plotted all the 4K channels for a particular single scan. And I have found that this what is the effect of this wideband? The effect of the wideband is it will stretch your data points radially outwards. Okay, so this you cannot find from your small GSB dataset. The reason behind is that we have provided only a small 33 mega bandwidth and a small indication time. Like it is only a 40 minutes of observation of the target. So to demonstrate how earth rotation synthesis and how a wideband observation will affect your UV coverage. I choose the wideband dataset. I first show you how for a particular single channel how observation of a target for a long amount of time cover your UV space, and now how uh, a long bandwidth will cover your UV space. So for a wide band, it will cover the UV space radially outward, and for a long time of observation, it will basically circularly or cover your UV space. So to summarize that, for the Earth rotation synthesis, it will cover the UV space like that. That is, it will circularly cover your UV space, and for a wide band data set, you will cover radially outwards. So our goal is to cover this, that is, fill up this UV domain as by as many points as possible, and that is basically you are synthesizing this UV plane with many number of baselines, and how to do this we use the Earth rotation and also the wideband observation. So this is basically all scans and 4096 channel. This is the total UV coverage of the whole wideband data set, which I observed for a particular on a particular day. This is a 8-hour observation with 200 megahertz bandwidth. So this is the UV coverage it will look like, and this is a nicely sampled UV plane, and from that you can get a nice image, which I will show you later. That is tomorrow. Now let us come back to use plot MS to plot the data in different way of our GSB dataset. So let's go back again to plot MS, and so whatever I have plotted here, I plotted here is the time versus amplitude and different scan. So in the beginning, I have observed flux, that is black, magenta is the phase, and then target and phase. But to notice is that this is the values of these amplitudes are very large, that is 16,000, 14,000. So these are basically RFI, right? And we need to, there are many, this is basically indicating you that there are some bad data in your observation, and you need to flag those. And how to generate this kind of plot? You just go to axis, you can in x-axis time, in y-axis you can just choose like this. Give me one second, where is amplitude? You can choose amplitude here, and in display you colorize by field. You go to data, everything is fine, and you can just click on this plot. Then this kind of plot will be generated. So I am not doing it here. Basically, it will take some time. So I am skipping it. You can generate this kind of plot in plot MS, uh, and every plot you can generate there. Okay. Let's go to F5. So next I have plotted for the flux calibrator before any kind of flagging what it looks like as a at the amplitude, how it looks like as a function of frequency. And as you can see, there are extremely large RFI, and it is again telling you this channel you needs to be flagged. Let's say. So we will not show you how to flag everything here, but we have generated a flag file, and we will apply it just in our terminal, and you will see that after flagging how it will look like. So there it is basically telling you there is a large RFI as a function of frequency, and I have plotted the phase calibrator here. It is again showing something is wrong, and then again for the target before flag, and again for the target, as amplitude scale are very high, and it is basically indicating that there are leftover RFI in your dataset. Here I have changed the plot. I have plotted the amplitude as a function of UV wave, and if you see that these values are extremely large, of the order of 1000, 1500, and these are basically again indicating that there are RFI. So these are the same plot for the phase calibrator, and this is the for the target, right? So how to flag it? So we have already created a flag file that has all we have also shared this in the Google Drive. We'll apply it here. There are lots of other flagging tools, but in this tutorial we'll just ignore that. So you have a flag file. How to do it? Let me demonstrate here in the terminal. Casa tutorial. Okay. So let's say INP flag data, right? So the visual in the vis file, this or the ms file is we have provided the ms file, and it is a in the mode we choose list int, and in the input file, this input file int input file, we provided this flag, right? And if I write this go, it will basically flag all the flag whatever is written in this list file. So we have identified beforehand which baselines are wrong, which spectral which channels are showing the RFI, and we have written that in this flag file, and we are just applying this in our data set. So that is what we have done so far here. uh, F5. So this is what we have done here. So we provide this flag file here, and we, if you just run go, it will flag the bad data set. So this is this is what it looks like after flagging. So what we have seen before that, this amplitude was very large, of the order of 14K 15K, but after flagging, what we found that the amplitude of the flux calibrator, which is 3286 as a function of frequency, has gone to like 30 to 40. However, to note that there is some wavy pattern that is basically tells you the gain, that multiplicity factor has a frequency dependent structure, and that is multiplied with your observation. So there is some gain, the effect of gain calibration is there. So we have not done any gain calibration, and we have not solved it yet, which Barnali and Preeta will show you. After calibration, it will be close to flat. So here is, it is the phase calibrator. Again, you see that it is, the order is now 10 to 20. Here these are not calibrated right now. These are before calibration and just after the flagging. But however, we come down to 10 to 20 scale from the 1500 like that. So moving on, this is for target, and this is for flux calibrator. Here I have plotted the amplitude as a function of UV wave. You have seen that this plot was showing large amount of RFI, but after flagging, it is more or less consistent. But note that these are not calibrated yet. So after calibration, it will look more consistent after the calibration. Okay, this is for target, and this is for the amplitude versus time. Now you see that there are still some leftover RFI here. This particular time range is probably problematic, but we have gone a significant amount of amplitude in this scale in the y-axis, where it was showing like 15,000 or something, but now it is close to 60 after flagging. So goal of the tutorial is to try to find out these gain terms, what Prasunda just show you. Find out this gain term and then calibrate your data set. And if once you get the calibrated visibility here, you can do some kind of imaging and try to find out how the sky will look like. That is the intensity distribution in sky. That is this ILA. This is the last task which I will show you tomorrow. So that is what I have told you, that our main motivation is that we, this, due to this multiplicative gain term, we have observed something corrupted visibility. We want to do that, we want to find out this true visibility, and for that we do sky based calibration. That is, we assume some model and we have the observation, and we try to find out what is this gain values. And once we have find out this gain value, we applied it, and then we can go back to this true visibilities. So this is it. I will stop here, and then Barnali will take it from here. Okay. So if you
So
have
if
any
you have
questions,
any questions, so please go ahead and
yeah,
ask to
you
Arnab.
can ask right now, or you can ask later also, whatever.
Yeah, tomorrow also. Okay, I don't see any raised hand or anyone is trying. So thanks Arnab for the tutorial, and you will take another tutorial tomorrow, right?
Yes, yes.
Yes, very nice. So you have chance to ask your questions tomorrow to
Hmm.
Arnab. So we'll go to our today's scheduled tutorial by Barnali, who is a senior PhD student at NCRA and doing extensively working on data analysis of this radio area for several years. So Barnali, can you share your screen? And
Yes, so can you see my screen? But I still cannot share the whole desktop which I wanted.
okay, so I can see your screen, so that is
Yeah,
fine.
but how? Okay, I'll unshare and share multiple times, and that will be a little bit
Yeah, I mean,
inconvenient.
that should work. Yeah,
Okay, so,
yeah.
do
I
you
think if you like,
sorry?
yes, I see you're scrolling, but I guess if you click on the separate window, that will also appear. If you just try now, in case you have other things on your laptop.
So do you see Casa now?
No, no, no. So it's
Yeah.
not
No, so
displaying.
you in the bottom of your zoom option there is means it will appear in the top side the what you want to share. You
It's
need
the
to click there
entire
and then
screen. Yes,
Uh,
it's
is
not a
this is this
particular
called
window.
desktop one or so?
I guess yes. It should be like entire thing.
So what
Now,
are you
yes.
seeing
yeah
now?
yeah. Now fine. Now
But are you seeing now the
Yes, yes,
slides?
yes, yes.
Okay. So you
no
can.
no no we see casa.
Oh,
Now
That's
slide
fine. No,
now
no.
slide.
Now we are seeing the calibration, your this slide. But before we were seeing the CASA thing. So I think it's
so you see the
working.
different window right now.
Different windows. Yeah, that's fine.
Right,
Okay. Then we are all set. Okay.
Yeah, full desktop is shared. You may try to do full screen once and we'll see what happens.
Okay. Sure. I'll try. You see full
Then
screen
fine,
now.
all right, absolutely all
Yes,
right.
yes,
And then next slide.
yes.
Okay, so this tutorial will be about calibration and radio data analysis, and you have already learned many of the things, so I'll go quickly over it. So Arnab has already mentioned about it. So this is the observed visibility, which Prasoon introduced this term in today's class. And basically we want to do calibration because what you record your telescope and what it is the real visibility is are related by something like this kind of an equation. So you want to find this term to recover the real visibility. Okay, and this term can be written, it has a one purely time dependent term which is a first varying in time, it is called complex gain, and this is called band pass. And these are again can be written as purely antenna dependent term, GIJ. Note that this I and J are antenna indices. This is the I8 antenna, this is the J8 antenna, and this is the bandpass term can again be written as two antenna dependent terms. So you have already heard this terms calibrators, but here I'm going to tell you what calibrators are. So if you have this equation, how will you find out this quantity? So you have this quantity, so you need some sources for which you know this true visibility. So such sources for which you know what the true visibility should have been are called calibrators. And the typical calibrators that one use are bright point sources. Because they are point sources, I think it will be very clear soon after maybe. For point sources, the visibility, this is constant in the UV plane, which is equal to the flux density of the source, and the phase is zero. This is a complex quantity. This will become very obvious once you write this one theta Jernicke theorem in the same most simplified form. But for the time being, just assume it that this is the case. If it is a point source, then it will have a constant visibility in the UV wave, and it will have a zero phase. So we want such a source ideally near our target field. And why is that? It's because Prasunda already mentioned about this ionospheric propagation effects, and these effects are different along different directions. So you want to calibrate the effects along your target field, and if your calibrator is somewhere here, suppose this is the ionospheric irregularity scale, then the calibration solution, the gain solution that you will get for the calibrators will not be same as what you want for your target field. So you want something which is close to this. Suppose in this direction your target is here, you want something which is close to your target field. So basically, you want the calibrator such bright point source with known flux densities near a target field, because these complex gains can have different values along different sky directions. But the problem is that most often we do not find such a source which is bright source, known flux density as a function of it's constant in time and known spectrum. All these properties, we do not find such a source always near a target source. So what people do is that instead of one such calibrator, we use two such calibrators. One is called a flux calibrator, which is the source which has all the required properties. It's a bright point source, you know its spectrum well, and it is, you know, it is constant in time, does not vary. And this will be your primary calibrator. You will use this to set the absolute flux density scale, and also to obtain the bandpass, which Pritha will explain today itself. And the other source is the phase calibrator, which is the source which is close to your target field, but you don't, it is a point source, but you may or may not know its flux density, and it's not necessarily required to have a constant flux density also. So you could, but the idea is that you will calibrate this source using the flux calibrator, and then you will transfer this calibration solution from the phase calibrator to your target. And this is the typical radio observation. You observe a flux calibrator first, followed by a phase calibrator, then you target for a longer time, then again the phase calibrator, and so on. So, and if you're, so basically how your flux calibrator is used to get the band pass and set the absolute flux density scale. So ideally, if the instrument is stable in sufficiently stable, you need just one such scan. But it is always good to have at least two such scans, because one is that you definitely need this calibrator scan, flux cal scan, and if something happens to this scan, then your observation will be in trouble. And the second thing is that it is only the ideal case that this bandpass will be stable, but often this bandpass, as I showed you already, it also has a time dependence, but not as fast as the gain solution. So it's advisable to have like more than one flux calibrator scan, and then you will have this phase calibrator scan. It's a more smaller interval of time, because this ionosphere effect, they happen at much smaller interval than the time scale at which the instrument changes its response. Okay, just again, so this tutorial, so I showed you that this visibility, observed visibility, and the target and the actual visibility are connected by this quantity, this gain, and which has a first varying time part and a slowly varying frequency dependent part. So this tutorial will purely be about how we determine this GIJT. It's called complex gain. So I don't think this is needed because you just learned it, but I will nevertheless, so you learned how to load data, how to flag data, how to check list stops, and I hope you quickly learned the Setzenski as well. So at this point, I would like to show you a little bit in CASA itself. If something happens, then I'll come back to the slides I had. That's why I put all the plots here. But let me once try to show you live. Okay. So back to CASA. So it is the plot MS. This is, so what you do. So Arnab just showed you the Setzenski. Setzenski is just asked.
Hello.
So
Yes.
Barnali, we can't
Yeah.
see your screen, so you have to share. I think you on yeah. Stop sharing
Oh,
the screen. That's right.
okay. Okay. This is desktop one. Can you see it now?
Yes. 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 Yes.
Okay. Okay. Yeah, please let me know whenever you can't see my screen. So the Setzenski is the task. So I said this. So just to remind you, this field ID 0 is for your flux calibrator. So using this Setzenski, you want to introduce the model. This spectrum for this source is already known, and you want to insert this model into your data. So I just to Setzenski, you have to specify the visibility. You can give any name you want, and you have to specify the field ID, which is 0. You learned it from your list ops, and then just press go, and Setzenski is gone. And you can, I already plotted it. You can see the model data, which is a nice, this is a model versus channel. I think I need to improve the this part. Sorry. Uh, okay. So what I am doing, you can these are not much important, so you can learn it later also. I just want to increase the size of those points. So this is the model. This is channel, which is effectively frequency. So you have inserted the model. Now you can proceed to calibration. So I'll come back to, so this Arnab has already showed you. So
So
after the
Barnali,
flagging,
I have a question. Like the previous plot in the amplitude versus channel. What is this amplitude? What it
This is the
specifies?
visibility amplitude.
It's the average one. In the frequency channel, you will have multiple visibilities at different.
This I plotted for visibility amplitude versus channel, though I haven't done any
Yes.
averaging.
Okay, you
This
haven't
is for
done
the
any
this is
average.
for
It's a
the model
particular.
data.
Raghu,
Yes.
see, this is a point source at the phase center. So as we'll discuss, so that has only single number will specify that for a given channel.
Okay.
Yeah. So okay, I want to show before I show you the other task. I am finding it very difficult to. Okay. Let me just show you a bit. So this you have already seen the flux calibrator and the phase calibrator, the visibility amplitude versus channel after the initial flagging, but without any calibration. So as I said, this tutorial will only learn how we do the calibration for the time dependent part, which is the complex gain. So for that, I choose a channel from the mid, which is say channel 100 from this band. Okay, and this model data for the flux calibrator, if I plot this for the single channel, then this here I have plotted UV wave. UV wave is nothing but this square root of U square plus V square. And you get this constant visibility amplitude for the model data and phase 0. This is because it's a point source. This is an important part. If you do not run Sedzensky for any of the source, then CASA will assume that that particular source has a flux density of 1 Zensky and it has a phase 0. So this is the assume model data for the phase calibrator when I did not run Sedzensky, because of course I don't know its spectrum. And this is actually correct because we already know that this is a point source, hence it will have a 0 phase like this. But this true flux density, we'll see whether it is 1 Zensky or not. We'll actually find out at the time of calibration. So this I could have shown you also, but okay, it's difficult to go here, and so I'll just show you the plot. So you already know how to plot in plot MS. So this upper panel is for the flux calibrator. The bottom panels are for the phase calibrator. I have plotted the visibility amplitude versus UPF for the single channel, one of the channel which I chose, which is the channel 100. I chose it randomly. You can choose any channel you want as long as it is not at the edges. And these are the visibilities, and the phases look most dramatic. As I said, the model data, ideally it should have a constant 0 phase as a function of UPF, but you can see the uncalibrated has all this random going from -180 to +80 phases, uncalibrated data. Similarly for the phase scale also, you can see this very random phases. So we'll see what happens to these phases once we do the calibration. Okay, now that we have come to only one channel data, so this bandpass has gone. So the equation is simplified to something like this. The observed visibility is equal to this GI star complex gain for the IAT antenna and JAT antenna and the VIJ sky, which is the true visibility. The strategy that we adopt is the following. What we'll do is that, so now we have two calibrators. One is the flux calibrator, other is the phase calibrators. Flux calibrator, we know the true flux density, we actually know the VIJ sky. So for that, we can easily calculate these quantities, GI and GJ for the flux calibrator. We'll also determine the same quantity, GI and GJ, for using the phase calibrator. Note that for the phase calibrator, although the phases are correct for the model data, the amplitudes are not. It is that we have assumed it to be 1 Zensky. Okay. As a result of that, since the phase calibrator model amplitude is not its real amplitude, the gain that we'll obtain, the gain amplitudes that we'll obtain for the two calibrators will be different. Okay. So you can, for example, consider these two equations. For the flux calibrator, it will be like FC means flux calibrator, PC means phase calibrator. So PIC observe this mod implies this amplitude of this complex number. And this is the model that we inserted. And this equation will give you this GI and GJ. Whereas for the phase calibrator, this is 1. You have assumed this flux density to be 1 Jansky. We don't know its true flux density. So this equation will obviously give you some different values of this GI and JZ using the phase calibrator. At this point, we make this assumption that these gain amplitudes do not vary significantly with time, which is a reasonable assumption because we expect the instrument to be reasonably stable, and ionosphere mostly introduces phases, not not affect the amplitudes of the signal. So so basically we call that these are the true amplitudes of the antenna gain, and these are the apparent amplitudes of the antenna gain. Now you can see that since these are the true gains, if this is the true flux, using the true flux density of the phase calibrator, we would have obtained the same gain amplitude as we had already obtained for the flux calibrator. Okay, I'm not sure if I am able to explain it properly or not, but I hope at least from the equation it should be clearly understandable. So you then you what you do is that you put this quantity GIGPC GJPC into equal to this in place of this, and then you get this kind of an equation. So you have already calculated this one, you already have this one, and you want to know this one. So based from this kind of an equation, you can infer the true flux density of the phase calibrator. Okay, now then once you get this true flux density of the phase calibrators, the amplitudes of the gain that you obtain using the phase calibrator data are properly scaled up, and then these you can use to apply on the target. So different tasks that you'll be used, Sedzansky you have already seen. It is used to insert the model data for the flux calibrator for whatever sources for which you already know the spectrum. Gain cal, this is the task that will calculate this GIGJ for whatever for the sources that what is you want to calculate. Flux scale is the task which will make this comparison between the gain amplitudes that you obtain for two different calibrators, and you from this comparison it will give us the flux density of the phase calibrator, and also if you choose it will correct the antenna gains obtained for the phase calibrator and give you a new calibration solutions. Apply cal, as it is very obvious from the name, is to apply your calibration. So and also it will interpolate, for example, for the target you have a solution here, you have a solution here. So for the target time you interpolate in time to apply on the target. Okay, and in addition you will use this plot ms task which you already seen, and plot cal to view different plots. Okay, so now I'll switch to casa again. Can you all see my casa screen now?
Yes, yes,
Okay,
right.
sorry. And this T-gate gain cal, what does it do? Does is that it restores the parameter from gain cal dot last. So if I have already run this task before, so it saves all those previously used inputs in this gain cal dot last file. I can even show you. So if you open this gain cal dot last file, it will show you all the parameters that you have used in your last round of gain cal. Okay, so T-gate gain cal will then automatically include this uh, input in your task. So there are several inputs here, but I will only mention those which are relevant at this stage. Visibility, it's of course the name of the file that you have to give. Cal table, this is the name of the output table where all the solutions will be written. It will be, you can give again any name you want. I have given field ID both 0 and 1. 0 is for the flux calibrator, 1 is the phase calibrator. It's because I already said I want to calculate the gain for both these two calibrators. And later I'll compare and find out the true gain is for the phase calibrator as well. And I have chosen because I am doing single channel calibration, I have chosen the channel 100. This is the way you write, you specify a channel. 0 is the spectral window. So in case of GMRT, there is only one spectral window, but if you use some other telescope, for example, the VLA, it will have multiple spectral window, and its spectral window will have channels. But anyway, in this case, the data structure is much simpler. You have one spectral window, and this is the 0th spectral window, and this is the channel number. Okay. And if you want, you can specify UV range, but I am not specifying any UV range. You can also specify scan and all these things. Solent is an important parameter. So solent is the solution interval. So if you have this data, this time varying data, so the minimum solvent is equal to the integration time, which is the 8 second. But then sometimes what happens is that it may not give sufficient SNR, so you may not be able to solve for all the antenna again. So you want to do some kind of averaging over the small timestamps and how much you will give. So it is kind of an optimum value you have to find. So how much you ideally, of course, if in the ideal world you will give the highest time resolution, which is 8 seconds, but then it will not give you sufficient SNR. So I have specified 2 minutes. You can also do 1 minute, but 1 minute to 2 minute kind of okay for these frequencies and this GMRT, this source, which I have as a phase calibrator. Flux calibrator, I know it's already bright, but phase calibrator, it's not that bright. So 2 minutes is okay. And then reference antenna. This is important because the the there is no meaning of the absolute phase. You always measure the relative phases. So like you, when you do this cross correlation also, because whenever you do this say GIGJ star, this will be like if you do the complex if you consider only the complex phases, it will be like I minus phi j. So the quantity of interest is not either phi a or phi j. The quantity of interest is the phi I minus phi j, the difference. So that's why you want a reference antenna. For the reference antenna, we'll assume that the phase for this antenna is 0, and all the phases will be calculated with respect to this antenna. And the scale mode, whether you want to solve only for the phases or both amplitude. I want to calculate both the amplitude and phase of the gains, because I think I have already explained, because I also need the amplitude. And solve mode R, this is a new feature in CASA 5. I don't know which version, it was not initially there. But this makes your solution robust to the outlier. So it will not, if there is an outlier, if you just, for example, if there is a distribution, there is an outlier, then the average will be very much affected by an outlier. But if you do follow a robust kind of algorithm, then it will not consider the outlier at all. So yeah, I want it to be robust against such outlier solutions, outlier point. And that is all. So I just run go, and sorry, it will produce a gain cal table, which I gave the name CCal.
So
Yeah,
Barnali, I have a question at this point. Can I ask?
sure.
So your the solution interval is 2 minutes, but my scan interval is much more than that one, 20 minutes or so. So the solution from this 2 minute interval, that will be applicable to all the visibilities within the scan range, right?
Within the scan, I did not get the question.
So you are solving this equation and getting conditions on phases,
Yeah,
and you are using this 2 minutes interval of data.
yeah,
Okay, right?
yeah.
And the solution will be applicable only to these 2 minutes of data, or you will apply that to the entire
Oh, no,
data?
no, 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 no. Sorry. Let me plot in time. Oh, sorry. This is not model. Okay, so it's like it's not okay, you can't see my hand, of course. So you suppose this is a 2 minute. So you, for this 2 minute of data, you get one solution. For the next 2 minute of data, you get one solution. For the next 2 minute data, you get one solution. That is how it's done. Then you kind of interpolate to get the correct dissolved visibilities. Am I
Okay,
clear?
but we don't have the phase calibration within this short time interval, but we are assuming that the phase calibration which we have done within this 15 minutes or so interval, that remains same. And we solve the phases within this 2 minutes of interval and apply to those data only. Is it correct?
I did not get again.
So when we do the phase calibration and we rotate the antenna to our phase calibrator, that is done after this 15 minutes of interval, right?
When I do
So,
what?
but
5 minutes?
when we do the observation,
You
Yeah.
are right. You are right.
yes, so we do the phase calibration at 11:09, and the next one we do at 11:14, something like that. Maybe if it is the scan two,
Okay.
right? Yes, within this 15 minutes time interval, which is my scan interval.
Yeah.
And now I am solving for the phases, but I only have information after this 15 minutes of interval. And I'm
So,
assuming that that phase information which I have after the 15 minutes, so that I am using to get the phase, to calculate the phases for individual antennas for these 2 minutes of interval. If I am clear, I'm not sure if I'm clear or not. But you see that what I calibrated, phase calibrate, that is after the 15 minutes, but I am solving within this.
yeah.
So why
No,
can't we?
no, Raghu, so the problem is that let's say you observe your phase calibrator, okay, and in for a fast, say 5 minutes of scan, that is the total 5 minutes, but you have data points every 8 seconds, right?
Yes,
8 seconds is your integration time. So every
yes,
8 seconds you are averaging. So you have 5 minutes divided by 8 seconds. That much amount of data points in within
yes,
these 5 minutes, right?
yes.
Now what we are doing, you are not using 8 seconds as the solution interval. Basically, that will not give you a sufficient good signal to noise ratio to solve this. So what you are doing, that you are using 2 minutes. So for the first 5 minutes, every 2 minutes you are getting a solution, and you are just interpolating for that scan. And again you are solving for the second scan for that 5 minutes, and you are getting solution for that scan, and you are applying that. You are correcting for that.
So we are interpolating between phase
Right.
calibration between these two windows.
Right. So no, you have solution for that first scan also. You have solution for the second scan also. If you plot the gain table, it will basically give you the solution as a function of time, and you will find that you have this solution for the first scan, and you have solution for the second scan. But then when you are applying to the target, you are then interpolating in between. Okay.
Okay, okay, yeah,
Oh,
okay. I think Barnali, you should
yeah, yeah.
continue.
I'm sorry, I did not, still
I mean,
didn't
we
get
can
you.
come back to this later. Okay.
Okay,
Now,
okay, fine. So, so we have run gain cal. Now you can actually see how your calibration solution looks using the task called plot cal. Okay. See, I haven't run the plot cal before, so that's why it says sorry, no task or save, because there is no plot cal dot last file here. So I'll have to uh, include it. So cal table ht1429980.gcal, which is the one that I have just produced. I will give x-axis as time, because this is the solution we solve as a function of time. So there will be time, and y-axis I want to see, say, amplitude, gain amplitude. I will also show you the gain phases. OLN is the polarization. Let's see only for one polarization. It is R, means RR and LL. I'm not sure if you have heard this term, but these are two like circular polarization. One is RR and one is LL. So here R means RR, and field 0, 1, 0 is for flux calibrator, 1 is for the phase calibrator. SPW, you don't need to actually specify SPW here because there is only one channel already. Subplot, okay, let it, okay, but I'll show you. It will plot 3 rows and 3 columns. Iteration, I want to iterate over antennas, and I'll also pick something called plot range to fix the y-axis, just to uh, make the change. It makes it visually more appealing also. Okay. So I hope I have said all these things. Then I will run go. So these are my gain tables. You can see the gain amplitudes are different for the flux calibrator, and these are the phase calibrator. You remember there is first scan was from the flux calibrator, then there were two scans which were for the phase calibrator. You can see the amplitudes are different. It's expected because I explained that for the phase calibrator, the assumed flux density is wrong. It's 1 Zensky. It already tells you wrong, because had it incorrect is indeed 1 Zensky, then you would have seen similar level of gain amplitudes for the both flux and phase calibrator. You can go next to see the various antennas, but I'll just stop here. And if you want to see the phases, you just write y-axis is equal to phase. Oh, sorry.
Plot range, plot range. You need to.
Thank you, Arnab. I was yeah. Okay. Yeah, plot range, because I set it 0.822, because but these are in degrees. The units are different, and that's why it doesn't show anything. I just want to bring your attention to this one. This is antenna 1. This was your reference antenna, and as I said, for the reference antenna, the phases have been set to 0, whereas for the others these are non-zero. These are all phases relative to these antennas. Okay, so
Just wait. Okay.
sure, yeah, sure.
Just to point out here to Roguda, that you see that there are these solutions, right? For scan 1, that is for flux calibrator, then scan 2 is for phase, and then again in the later one. These are your gain solution, and you are basically taking the solution every 2 minutes. That's all, and then you will apply those things for that particular scans. Okay, so I hope this clears something.
Yes, okay. Go ahead.
Okay, thank you. And next, as I said, so we have calculated this GIN GJ star. We have found the GITs for the antennas using both calibrators. Now we need to find out the flux density of the phase calibrator. Okay, and that will be done using the task flux scale. Okay. Okay, so this is the again visibility file. Here, cal table means as you can see, the name of the input calibration table. So by the way, Arnab already mentioned, but I just want to reiterate is that every task or each of the tasks has very nice documentation in CASA. So for any input, if you are confused in anywhere, you can just go to the NRO web page dedicated to CASA and see all those inputs in detail. Okay, so cal table here is the cal table where this amplitude solution for these two sets of calibrators are there, which we want to correct now. Flux table is the name of the output table where I want this corrected gain amplitudes, because once we learn this flux density of the phase calibrator, then the amplitude of the gain which we calculated for the phase calibrator will have to be corrected, and this stars will internally correct for it and write a new calibration table, which I have given this kind of a name. Reference is the source for which you know that the gain solutions are correct, and transfer is the one for which you want to estimate the flux density by making this comparison. In our case, reference is the flux calibrator and transfer is the phase calibrator. Okay, let me make sure there is no okay. So this will create a table called ht142990.flux, as I given the name, and also see the logger. It will give us the flux density. This is the name of the phase calibrator. It has around 2.3 Jansky. Okay, so we got the flux density of the phase calibrator, And now let us check the gain amplitude again. I gave this flux and I want to see the amplitude because phases there will not be any changes. And of course, point it to 2. You can see it has come almost at the same level. I have a better slide which shows the thing at the same. Yeah, this one. This is after flux scale and this was before flux scale. You can see this has come almost at the same level after you do the flux scale task. Okay, so also use up to see the logger to get the flux density of the phase calibrator. And now you have to just apply on your field. And the task that is there for us is apply cal. You have to give, here I am not applying on the target because we, or you can apply on the target and just to check how it looks after the single channel calibration. But I think Pritha will apply all this flux table and bandpass calibration table together on the target as well. Here I'll only show you the calibrated data before and after flag, how it looks before calibration and after calibration. So I have specified hence the field ID only for the calibrator, which are 0 and 1. The channel I have specified. And this is the table that you want to apply. Gain table means the cable table that you want to apply. And if you run go, it will apply the table. Now, x-axis I want to put the UV wave. Let us see how it looked before calibration. This was my amplitude, but as I said, the phase looks more interesting than amplitude without calibration. These are my phases, and I hope, and these are my phase after calibration. So you see, you can, I hope you can see the difference. I'm sure you have seen the difference. And for the phase calibrator as well, okay, this I showed you the corrected data, but let me show you the data. This is the phase when you don't do calibration, and this is how it looks after you calibrate your data. Okay, this is, there are some RFI at the low UV which you need to flagged further, but basically the first round of calibration is okay. You can see a nice 0 which you expect for a point source. And I'm glad that I finished my tutorial almost on time. So just to convince you, in case you have not been convinced already that calibration is important, I will show you a this figure. So this is the, if you learn imaging probably tomorrow. So if you just take the uncalibrated flux calibrator data and do the imaging, this is what you will get. Here is absolutely nothing. But if you do the calibration, this event, the single channel calibration and do the imaging, you will see this nice source, nice point source that you expect uh, for your flux calibrator. So yeah, that's it. Thank you. Bye.
Thanks, Barnali. The questions.
May I ask some naive question? So, Barnali,
Yeah.
you mentioned first round of first round of calibration. So, when do you move to next round? Means, what do you change between first round and next round?
Okay, that's a good question. Something which I should have mentioned. So, in reality, what happens is that often, so you do the first round of flagging, which Arnab showed you, and do the calibration. Then you again check your data, corrected data, and often you can see then find you can then see further corrupted data or RFI. You then do the more flagging, and if you do the flagging, then the statistics have changed and you have to recalibrate your data. So every time after a particular round of calibration, you must check your data and see whether there is any further bad data. If there is any bad data, do the flagging. If you do flagging, you must do the calibration again. So this calibration and flagging loop continues until in the latest, until after the latest round of calibration, you do not see any bad data in your uh, corrected data column. So
Okay,
that's
okay.
where you stop and go and proceed to next imaging or whatever task.
Right. Another small question. So, in for the flux calibrator, you expect your flux to be a stable high value, which
Yeah.
is we know,
Yeah.
and for the phase calibrator, you expect your phases. Your model expect your phases to be what, zero or some constant value?
0.
Zero.
Yeah.
And for the flux calibrator also,
Yeah, it's because both are point sources, it will be 0.
point sources at the phase center. Okay, okay,
Yeah, point source at the phase center, it will be 0.
okay, okay, okay. Thank you.
So if some part of the signal it is RFI dominated or not, that can be only identified after the first round of calibration, is it?
Yeah, this is often the case actually. So only the very bad extreme kind of RFI you can see from your data. See what happened is that often in your data, so suppose for two antennas the gains are very different, then in your normal data you will see different offsets kind of thing. So one may be quite high, one may be quite low. You cannot flag them, or you cannot kind of say whether this is because the gains are different or whether this is due to RFI. Only after the first round of calibration you can kind of point out, okay, this is not due to gain difference, this is due to RFI, and maybe you can do a more stricter flagging. So
So
that's
for the second round, we remove the part which is RFI dominated, and for the solution, so where we start from the end of this corrected data after the first round, or we go back and start at the scratch.
you have to start from gain cal itself. In this case, set sense case, okay, you just inserting the model, but you ideally you delete your cal tables, but often casa operate, but you for to be on the safe side, you delete your cal tables, you do clear cal to correct remove your corrected data column and start from gain cal.
Okay, okay.
Yeah.
Okay, good. And Arnab has a question, so you can
Am I audible?
Yeah,
yes,
yeah.
yes.
Okay, thank you. So I have a question for Arnab. So, so what? So, so what we have seen right now. So in the initial stage, there are some high RFI data in the amplitude plots, and then we have flagged those data, importing some external .flag file and processing
Right.
in Casa.
Right.
So are we actually flagging some data for some antenna, or we are actually flagging the entire data set detected by an antenna, or
So
any sort of spectral range? So
okay, so the basically what we have done is that we generated this flag file. You can open it this flag file in Emacs or gedit or something, and you can find out what is written there. So what Barnali did that so this she generated this flag file. She iterate different antennas, different baseline, try to find out which baseline is wrong, which antenna is wrong for particular scan and everything, and she write it in this flag file, and then she flagged it. So let's say a particular antenna is flagged, then particular antenna is showing some bad behavior, then that antenna is completely flagged for the entire observation. Or let's say a particular baseline is showing some corrupted data or something wrong, then that baseline is flagged for the entire observation. That is what we have done so far. So we have not show you in detail how to flag it and use different kind of a flagging algorithm and how to find out RFI, because that is extremely time consuming part. So that is why we have generated this flag file and we have provided you, and you have just applied that during our analysis. That's all.
Yeah, can I
uh,
add a little bit?
Hmm. Go ahead. Yeah.
Yeah. See, basically, you have to ask the question, what is RFI? RFI is something which is man-made, right? So, for example, you are detecting a signal which is 1 Jansky 10 to the minus 24, 25 watt. And so you go to the observatory near to an antenna, switch on your mobile, which is radiating at 1 watt, 10 to the 20, 25 times than the signal that you want to detect. What will happen is that the antenna nearby will catch up most of the signal. It will also catch up in the frequency in which your mobile is radiating. and the time on which for which you have kept the mobile on. So it basically means that these RFIs can be localized in time, frequency, and which antenna, near to which antenna the RFI has the source. Obviously, if there is an antenna nearby, another antenna nearby, that may get also affected for some time. Sometimes you may also move with your mobile phone or whatever the source of RFI, then the signal will move from one antenna to the other, right? And sometimes the antenna may not be working. So then it is giving all zero. So that we don't, it's not an RFI, but we have to also take care of that antenna. It's not receiving any signal from the sky. So all these uh, contribute. It can also be a satellite which happened to be there for 5 minutes of your observation, radiating to all the antennas in your array. So all those 5 minutes data is gone.
Okay, so we basically keep those data completely out of our analysis, right?
Yes,
Yes.
it is always good to remove bad data than keeping it.
Yeah, yeah. Okay.
It's like if you have a naughty boy in the class, you throw him outside.
Yeah, yeah. Understand.
Are there any more questions? I don't see any more questions.
Maybe I can ask a very small question. So,
Yeah.
Barnali, you did this whole thing for one channel only. So,
Yes.
what will happen to the bandpass thing? It's like it will be followed up later, or will stop?
Yeah, Pritha, after today itself, the last tutorial session will be about how we find out the frequency dependent gain part.
Okay, thank you.
I want to ask one question to all the participants. So, did any of you actually install CASA or not? Maybe you can write in the chat box.
Yeah, okay, that we are not sure about. But yeah, they can always see the tutorials and how to install and apply the task and check later also. So before we finish, so I have a question to Arnab. So you talked about these two types of observation, the single scan and
Right,
multiple
right,
scan.
right,
Uh,
right.
so which type of observation we need to choose, and it is must be preferable for a particular set of observation, the scan mode only.
Okay, so the question is that so basically you want to synthesize a big single telescope via a interferometer, right?
Yeah.
Now you have some discrete points, and those points are basically your baselines, and that baseline is basically correlation of two antennas. Now basically you want to fill up this UV space by as many points as possible. Remember that in imaging, the PSF, that is the point space function, is basically the Fourier transform your sampling function. Sampling function is basically whatever you are getting in your UV domain. So what are the data points are lying in the UV domain. So your goal will be like you sample your UV domain, you cover your UV space as by as many points as possible so that it is nearly complete. And if it is nearly complete, then your synthesized image will be good and will be free of some PSF structure and all other stuff. So the ideal case should be you observe a target for a full synthesis hour, like it rises at that time, it goes above some elevation, and it sets. So if you observe for 8 hours and you divided that 8 hours in some scans, let's say 10 scans, and some phase calibrators can in between to calibrate, and you have, if you observe it for a wide band, then your UV coverage will be completely, more or less completely filled up, right? It will cover that in circularly for the Earth rotation synthesis, and it will cover radially for the wideband data set. So that will be your ultimate goal, that you try to cover this with the maximum amount of data which you are able to take. But there are also caveats that it will be huge data set and probably you will not get that much amount of time and all other stuff. But whatever we provided here, this GSB small data, this is just a single scan. We just take a small single scan from a wide data set, and we have provided this just to demonstrate. So this is not the scenario for all other observation.
So are there like any observation which are observed or proposed to be observed in single scan mode for specific reason?
No, see, if you have a single scan, maybe your source is extremely bright and you can see that source. That is not an issue. Uh, let's say a source is a 10 Jansky or something like that. You can say that, okay, give me 2 minutes of observation. I can reach a RMS, which is say 1 Jansky. So I can detect the source with 10 sigma. So 10 Jansky source, I reach on 1 Jansky. But the problem is that you cannot make a good image, because the 2 minute scan, your UV coverage will be extremely sparse, right? So your sampling function is extremely bad. And when you do the Fourier transform of sampling function, your PSF, so basically your PSF is convolved with your source.
Yeah,
You need
just
to deconvolve your PSF. So your PSF is extremely bad. You cannot do a good synthesis imaging, right?
Right.
yeah.
Right.
So I will just add. I mean, because there is one case where you actually do this. So imagine that. So you have this calibrator sources, right? Right. So say 3C147 is one of the calibrator source, and it's essentially a radio galaxy which is far away from our galaxy, right? So if you want to observe, if you observe this in the L band, which is near 1420 megahertz, there is enough H1 in our galaxy which will get absorbed as the light from this source comes to us. Okay, and maybe you want to observe that H1 image against a point source, which is 3C147, which is a very nice point source at the phase center. Okay, so now you see all of your problem of imaging and deconvolution goes away. You don't need to even deconvolve the image. It's a point source at the phase center. You can just look at the visibilities, and even then also you can make the spectra out of it. All the visibilities add in phase at the center of the field of view, right? So phase is 0 for all the visibilities.
Right.
So now, if you want to it's a very strong source, say 20 Jansky. So you can make a 5 minutes observation, you will get a reasonably good spectra. And that type of observations are done for some of these calibrator. I think Nirupam and Nisim, they looked at many of these.
Bright radio galaxy.
Yeah, they don't look, I mean, you look at direction of the bright radio galaxies, but you really map the H1 in our galaxy.
Yeah.
In absorption.
Okay, good. Are there any other questions? Okay, if not, you can always come back to with the questions to the next tutors, and also you can go to the Slacks and type your questions there. So let's talk now. Thanks, Barnali, for your